Saxon's Calculus Lesson 95 is about the mean value theorem, application of the mean value theorem, and then proof of Rolle's theorem, which I tend to not do the proof of. So in part A, the mean value theorem, it is a lot of wordiness rather than showing you things. So the main boxes on page 462 are the maximum and minimum value existence theorem. So if f is continuous, no gaps, on a closed interval between a and b, then the function f has a maximum value called m and a minimum value, the lowercase m, on the interval between a and b. We've talked about that one before. Intermediate value theorem. If function f is continuous on the closed interval between a and b, and capital N is a number between the function of the maximum and the function of the minimum, then there is at least one number called c falling between a and b inclusive, for which the function when you plug in c gives you n. Then they move into the mean value theorem, which on page 463 is the box that contains that information. Now there's a step 1 and 2 before that, but it's also embedded in the theorem itself. So the mean value theorem says, if the function f is defined, that was step 1, and continuous on the closed interval of a and b, that's also step 1 there, and step 2, it is differentiable on the open interval between a and b, then there exists at least one number called c somewhere between a and b such that the normal derivative formula works, where we have the function plugging in b minus the function plugging in a being divided by b minus a. Now, on the next page, example 1 says, demonstrate an understanding of the mean value theorem by using the function x squared minus 2x minus 8 on an interval between -2 and 1. Now this one I can show some numbers. So it said we've got f of x is x squared minus 2x minus 8, and they want me to show between -2 and 1, but of course, because it's in those brackets, it's not including those. So the first question is it continuous? Well, this equation, x squared minus 2x minus 8, is a parabola. There's no reason to expect a gap in a parabola. Check. Part 2, is it differentiable? All right, so if I derived the formula, I would get 2x minus 2, and since I can plug in values, then yes, it is differentiable. Okay, so now I'm going to backtrack and find out what happens when I plug in -2 and 1. So if I plug in -2 to this original equation, I end up with an answer that is 0. When I plug in 1 to that equation, I get an answer that is -9. Now, rather than my showing you the plugging in, I expect you to have done it on the calculator, do it in your head, however you're doing it. So now we see if we actually have a slope. So we fall into the original one, f of x, which gave us 0, minus the second one, which gave us the -9, so that turns that into +9, being divided by the -2 minus 1, which is -3, so 9 divided by -3 is -3. Okay, so I do have a slope that is -3. So the mean value theorem does guarantee that there is a value somewhere between -2 and 1, which provides me a slope, which is -3. Now they say if you want to finish with this having already derived it, to see where setting this equal to the -3 would get you, well, you can get the value that x comes out to be, -1/2. So at the -1/2, you get the slope value of -3. It didn't ask you to do that, but you can. Example 2, the value of a function, I'll write it, but f of x equals 1 over x squared minus 1. that equals 0 at -1 and 1. So -1, 0, 1, 0 is basically what that's telling me. So if I'm picturing that, obviously those are dots at 1 and -1. Okay. There is a line then connecting those 2 points. It's a horizontal line, and the slope for that line will be 0. So the mean value theorem to find a point between them for which the tangent of the graph of the function equals 0. All of that was the question. I'm going to reread that last part. Use the mean value theorem to find a point, I don't think I said that before, between the -1 and the 1 for which the tangent line of the graph of the function is 0. Okay, so here's my problem. The mean value theorem has to be continuous. And so is it continuous between -1 and 0? Well, if I try to plug in the 0, I get 0 in the denominator, which is a problem. And so it fails the continuous test. So no, the mean value theorem cannot help me at all. Example 3. Demonstrate an understanding of the mean value theorem by using the function f of x equals x to the 2/3 and the interval -8 and 27. Demonstrate the understanding using the function and that interval. All right, so is the function continuous between -8 and 27? Well, if I plug in any number between them, I'm getting answers, so I'm good to go there. Now I'm going to check to see if it is differentiable. So that gives me 2/3 x to the -1/3, which would be basically 2/3. The negative is bringing this part down, and that's making it the cubed root of x to the 1st. Should be. Wait a second. No. 1/3. Yep. Should say cubed root, and they don't have that. But anyway, all right. So if I plug in the 0, I have a problem in the denominator. Oh dear, that means it's not differentiable. So the mean value theorem doesn't help me. Can't use it. Example 4. The function f of x equals the absolute value of x minus 1 is equal to 0 at -1 and 1. Well, that's that same picture. Does the mean value theorem imply that there exists a number c somewhere between them so that the derivative of c would give me a 0? Now, absolute value should create a v here, but the -1 drops it down, and so here is the actual picture. So is it continuous between the 1 and the -1? Yes. Is it differentiable? No. So the mean value theorem fails. I can't use it. Then in part B, they say, what are the applications of the mean value theorem? All right, so they state these things, these two theorems, and then they try to prove them, and their proof to me is just kind of laughable. Anyway, the theorem says, if the derivative of a function equals 0 for all real values of x, the function is a constant function. In other words, it comes from a constant. A more formal statement of this is if derivative of f of x is 0 on an open interval called I, then the original function of x gives you the constant on I. Okay, duh. And then they basically just plug in b's and a's and the c and sub it in for the 0. You can see what they're doing there, and it just comes right down to f of x equals c. Okay, then the next theorem. If two functions, one f and one g, have the same derivative for every value of x, then the functions only differ by a constant. Okay, well that makes sense. And then they write out the theorem, and then they do kind of the same thing. They do a proof where they're plugging in things, and it's just C. Okay, then the proof of Rolle's theorem is section C, and it tells you that Rolle's theorem is a special case of the mean value theorem, which ultimately wasn't extremely helpful. But anyway, so it's a special case of it for which both the function plugging in A and the function plugging in B both give me 0. So this theorem is easier to prove than the mean value theorem. And then they walk their way through. It has endpoints. There are values of x for which it does not exist, and there are values of x for which the derivative comes up 0. Therefore, the derivative of C definitely gives you 0. Yeah, I found that so incredibly helpful.